Today I will discuss the previous lectures, what we done in the silo theorems and its problems. Today we will discuss some of the problems related to silo theorem. Majorly, today's lecture is based on the simple group. What is simple group? A simple group is a group with no non-trivial proper normal subgroup. Then we say that it is a groups are simple. In the last class, we started with some of the silo first and second theorem. What is silo's first theorem? Let G be a finite group of order n. It is in terms of p power k into q, where p is a prime number and q is any positive integer. And also you know that the relation between p and q, that is GCD of p and q, must be 1. Then for each I 1 less than or equal to I less than or equal to k, then G has at least one subgroup of order pi. These things we already proved the theorem, and also we discussed about the p subgroup. A subgroup H of a group G is said to be P subgroup if the order of each element H is a power of some prime number P. After that, we discuss about the silos P subgroup. Let G be a finite subgroup and P be a prime number such that P power K, that is prime number to the power of K, divides order of G, but P power K plus 1 does not divide order of G. Then G must have a subgroup of order some P power K. This subgroup of order P power K is called a silo subgroup. And also we given some examples related to S3 and S4. And also we discuss about the conjugate of a subset of S of a group. Let S be a non-empty subset of a group G. Then the set X inverse Sx is equal to set of all X inverse Sx such that S belongs to S is said to be a conjugate of S. This is determined by this element X is in G. And then we discussed about the normalizer of a set. Let S be a non-empty set of a group G, non-empty subset of a group G, and K is a subgroup of G. Then normalizer of S in K is the set. It is in the form of Nk of S, that is set of all X belongs to K such that X inverse Sx is equal to S, small s. Then Ng of S is equal to normalizer of S also. And also we discuss some of the note related to this. And after that, we discussed the one of the lemma that P be a silo P subgroup of a finite group G. Then P contains all the elements of N of P, which are of the order A power of P. And after that, we discussed the two silo theorem, silo second theorem, as well as silo third theorem. In this, both the statements let G be a finite subgroup and P be a prime number such that P divides order of G, then all the silo P subgroup of G are conjugate of one another. That we already proved. And the third theorem says that G be a finite subgroup, P be a prime number such that P divides order of G, then the number of silo P subgroups is 1 plus P. Here, M is some non-negative integer such that it is in the form of 1 plus MP that divides the order of G. That is known as silo third theorem. These three theorems we discussed in the previous classes. And also we given some examples related to silo subgroup, silo 3 subgroup, silo. Depending on the prime number, we discuss the problems also. Is it correct? And also we proved one of the theorem. If G is a finite group and P be a prime number such that P divides order of G, then we prove that silo P subgroup of G is a normal subgroup of G if and only if P is the only silo P subgroup of G. This theorem also we proved in the previous class. Now we will today's class we will discuss about the simple group. I already mentioned the definition of simple group. This is the one of the problems related to simple. Show that no group of order 30 is a simple group. Simple means it is a group is said to be simple. First, how to prove this? How to solve this problem means first you can take G be a group, such that first you can make that order of group G can be in terms of prime product. What is prime product here? 30 can be written as 2 into 3 into 5. Then you know that in the silo third theorem, the number of silo 5 subgroup is in the form of 1 plus 5m divided by 6. Therefore, the number silo subgroup of M must be 0 or 1. Suppose if M is equal to 0, then what happens here? M is equal to 0 means this is 6 divides 1. Therefore, G has a 5 silo subgroup, it is 1. You know that 1 means which is a normal subgroup of G. If M is equal to 1, then G has a silo 5 subgroup. Then this becomes 1 plus 5, that is 6. This 6 can be written in terms of the subgroup is in the form of H1, H2, H3, etc. H6. We can represent that 6 silo 5 subgroups in the form of H1, H2, H3. And also we know that the intersection of all these must be equal to 1 because you know that it is an identity. Therefore, you know that I is not equal to J, then 5 subgroups contain 24 elements. Means already 6 will be there in the 30. It is reduced, 6 is reduced means it becomes 24 elements of order 5. And there is one element of order 1, then the only remaining is what is that? Here 24 and 1, that is 25. Then the remaining G can be order 2 or 3. The number of silo 3 subgroup, again it is in the form of 1 plus 3m, then such that 1 plus 3m divides 2 into 5, that must be 10. Then M must be 0 or M must be equal to 3. This is the only two possibilities here. Therefore, if M is equal to 0, the number of silo 3 subgroup G must be 1. You already seen in the 3 silo subgroup and 5 silo subgroup we discussed the previous class, which are also normal subgroup of G. Then again here if you put M is equal to 3 here, then 1 plus 3 into 3, that is 10. Therefore, the number of silo 3 subgroup is 10. Then again, we can represent this in a silo subgroups, that is H1, H2, etc. H10. The 10 can represent silo, that is H1, H2, etc. H10 are the silo 3 subgroups of G. Again, the intersection of the order of HI intersection HJ must be 1. The silo 3 subgroups contains 20 elements of order 3. And also you've seen that hence 10 silo 3 subgroups 20 elements of order 3, which is not because the order is only 30. You already got 25. Again here another 10. Is it possible? No. That's why we say that which is not possible. Then G contains either a normal silo 5 groups or silo 3 subgroups. Means G is not a simple. This is the one theorem. Similarly, show that group of order 108 is not simple. What is the first step? First, we can make this into product of prime powers. That is, order of G can be written as 108 here, then 108, then 108 can be written as 2 power 2 means 4 into 9, 4 into 27, you get 108. Therefore, we get silo 2 subgroup and silo 3 subgroups. The number of silo 3 subgroups is in the form of 1 plus 3m. Again, it is divided by 4. Therefore, m must be 0 or m must be 1. If m is equal to 0, then G has a silo 3 subgroup of 1, which is a normal subgroup. It is in the form of 3 power 3 divided by 1. 3 power 3 means 27 divides 108 means 108 divided by 20. But 3 power 4 does not divide. This is divides, not divided by. You must remember is 3 power 3 divides 108, but 3 power 4 does not divide 108. Hence, G is a normal subgroup of order 27. If m is equal to 1, then the silo 3 subgroup is in the form of 1 plus 3m. 1 plus m is equal to 1 means it becomes 4, which is of the order is 3 power 3, that is 27. Then you know that order of H1 intersection H2 by order of H1, then order of H1 intersection H2 must be 1 only, 1. Here we having a 3 possibilities, 1, 3 or 9, because 1 divides 27, 3 divides 27, 9 divides 27. Then order of H into H1 into H2, you already know this theorem. Then we can use this order of H1 into order of H2 divided by order of H1 intersection H2. This must be 27 into 27. It is greater than 108. Then order of H1 intersection H2 must be 1 or 3. Then order of H1 H2 is greater than 108 means, but our order of a group must be, it is 30 only, which is a contradiction that H1 and H2 are the subgroup of G. Then definitely order of H1 intersection H2 must be 9 or p square. You know that H1 intersection H2 is a one element is contained, therefore it is a normal subgroup of G. We already proved this. Then H1 is contained in the normal normalizer of H1 intersection H2, and H2 is also contained in the normalizer of H1 intersection H2 means definitely the product, that is H1 H2, is also contained in normalizer of H intersection H2. Therefore, order of normalizer of H1 H2 is greater than or equal to order of H1 H2. Then here order of H1 and order of H2 is 27 into 27, but we have taken this order of H1 H2 is 9 here. Therefore, this must be 81. Then a normalizer of H1 intersection H2 is a subgroup of G, we already known, and also order of n of normalizer of H1 intersection H2 divides 108. Now, normalizer of H1 intersection is G, means you know that H1 intersection H2 is a normal subgroup. Normal subgroup with respect to normalizer of H1 intersection H2. Therefore, means it is a normal subgroup means definitely it is a not a simple. These are the two important theorem. You must three important problem. You must work it out. Similar type of problems you can do it. Is any doubt?
No, sir.
Okay. Next, one more theorem. Let G dash be a commutator of a subgroup of G. Then G is abelian. Then if and only if G dash is equal to E, then E be a identity element of G. Let G be a subgroup. M is equal to means G is a commutator subgroup. Commutator subgroup of G means what is that? Commutes with each other. That is the definition. What is abelian? AB is equal to BA. If these two conditions are there, then G dash must be identity element alone. That if it is abelian, then G dash must be abelian. Here, let G be a subgroup. M is equal to set of all xy, x inverse, y inverse, xy belongs to G. G dash is a commutator of a subgroup. This is the definition, you know, the commutator subgroup. What is G is abelian? If it is two elements, xy belongs to G means xy is equal to yx. Then definitely the elements of M commutator subgroup having M is equal to xy, x inverse, y inverse. You know that in a group we can interchange the elements here. Yx inverse can be written as x inverse y. Therefore, because it is a subgroup, then here x into x subgroup, x into x inverse y into y inverse. Then this become x into x inverse into y inverse. We can apply a associative law here. Then this become x into x inverse into y inverse. You know that x into x inverse become identity. Then y into y inverse is also identity. Means M is equal to identity means definitely one of the element is G dash must be identity. What is the next converse we are proving? You can choose is it abelian and also let G dash is equal to E. Then you get commutator. Sorry, xy is equal to x inverse y, then xy into yx inverse. This can be using the reverse law of inverse, that is xy into yx inverse. You know that it is the identity. Then you can transfer here to right hand side, that is yx inverse become yx, or multiply both the sides yx, you get xy is equal to yx, means it is an abelian. This is the simple theorem you must remember. And one more theorem, I am not proving this, but you must remember the statement. Somewhere we can utilize, let G be a group, G dash be a commutator subgroup of G, then prove that G dash is a normal subgroup. You can prove easily. And the quotient group G by G dash is a commutative bar abelian. Quotient group G dash is a normal subgroup, then G by G dash is abelian. How the elements is look like in the quotient group? It is in the form of coset. You can use the coset form. You get a proof for this. And also normal subgroup. Normal subgroup is denoted by N of G. Quotient group G by N is a commutative if and only if G dash is contained in N. Because what is G dash? G dash is a commutator subgroup. Commutator subgroup containing xy, x inverse into y inverse. Then definitely it is a subgroup. Then one more theorem, that is a subgroup H of G is contained in G dash. Because G dash is a commutator subgroup of G, then definitely this subgroup, the subgroup of a commutator group is also a normal subgroup. These are the things you must remember in the first chapter related to Solo's theorem. Now we will discuss the normal series.